Hi, hi guys. My name is Samuel Jasper. I'm from CSC department. My topic on data structure for AIT Tech Talk is on graphs, convolutions, and neural networks. From graph filters to graph neural networks. Let's see what is graphs and convolutions and neural networks is all about. Introductions. Graphs are a natural way to represent relation data where nodes represent entities and edges represent the connections. Convolutions, which are used in CNNs for images, help us capture local patterns, but graphs are irregular, so we need specialized operations. Neural networks allow us to learn complex patterns from data. By combining graphs and neural networks, we can learn representations that capture both the features of nodes and the structure of their connections. This is essential for tasks like social network analysis, molecular property prediction, and link prediction. Graphs. Graphs are a data structure that represent entities and relations. Graphs consists of nodes which is known as vertices represent entities and edges links represent relationships between nodes. For example, social network nodes are represented by users and edges are represented by friendships. Citation networks. In citation networks, nodes are represented as papers and edges as citations. Molecular graphs, nodes are represented by atoms and edges are represented by chemical bonds. Neural networks. Neural networks are also known as NNs, are computational modules that learn high dimensional representations from data, typically designed for Euclidean data such as images, sequences, and etc., but can be extended to graphs with specific operations. Convolutions. Convolution is a mathematical operation used to extract local patterns from structured data. Traditional convolution in images which operates on pixel grids to detect edges, textures, and features. Graphs basics. Graph consists of nodes, edges, adjacent matrix, and I will look into examples after that. A node is a represent entities in a graph. Each node can have a feature and an attribute. For example, a user profile in social media network or an atom type in a molecule. Edge, it is also known as a link, represents relationships or interactions, can be directed or undirected, and weighted or unweighted. For example, a directed edge, paper A cities to paper B. Weighted edge, strength of friendship between two users. Adjacency matrix, a square matrix used to represent graph connectivity. Aij is equal to 1 if node I is connected to node j, otherwise 0. Weighted edge uses the weight instead of 1. It helps in matrix operation for graphs algorithms and GNNs. The example applications are social networks, citation networks, molecules, and traffic networks. Graphs are composed of nodes representing entities and edges and representing relationships. Nodes can have attributes and edges can have weights or direction. The adjacency matrix encodes the connections and is essential for computation in graph neural networks. Examples include social network, citation network molecules, and traffic networks, where graphs capture the underlying relationships and structure. Let's understand what graph filters is and is all about. Graph filter. It generalizes signal processing operations like filtering in audio, images to graph structured data. It operates on node features by combining information from neighboring nodes. The main purpose of graph filter is to enhance important signals or reduce noise in the graph. Laplacian graph. It is central to graph filtration. It is defined as L is equal to D minus A, where D is equal to degree matrix, which is diagonal and shows node degrees. A is equal to adjacency matrix. It is also and it consists of low pass filter on graphs, smooth feature across neighboring nodes. It reduces variation between connected nodes. For example, in a social network, similar users' feature interests become one more aligned after filtering. Graph filters extend traditional filtering techniques to graph structured data. They operate on node features by aggregating information from neighbors. The Laplacian matrix encodes the structure of the graph and enabling low-pass filters to smooth features across nodes or high-pass filters to highlight the differences between them. This is particularly useful for pre-processing features before feeding them into graph neural networks or detecting anomalies in graphs. Graph convolutions. Why graph convolutions? Before that, let's see what is graph convolution is all about. It is a traditional convolution in CNNs works on grid, such as images and videos. Graphs are irregular, where nodes may have varying number of neighbors and with no fixed order. Graph convolution is designed to aggregate information from a node's neighborhood considering the graph structure. Spectral domain convolution. Based on graph signaling process, graph Fourier transform is applied using eigenvectors of graph Laplacian L. Here we can see the formula for graph Fourier transform where we can apply it on domain convolutions and etc. Spatial domain convolution. It operates directly on nodes and neighborhoods, more scalable. Here we can see the node formula where it is applicable on spatial domain convolution. The intuition behind convolutions are each node collects information from its neighbor and stores in the database, and also it consists of multiple layers where node gathering information from multi-hop neighbors. It also analogs to how computer neural networks filter capture local pixel neighborhoods. Graph convolutions generalize computer neural networks to graphs. Because graphs are irregular, each node aggregates features from its neighbor. In the spectral domain, we use graph Laplacian eigenvectors to define convolution. In the spatial domain, we directly aggregate neighbors featuring using sum, mean, or max functions. Multiple layers allow nodes to capture information from further away in the graph. This process is essential for learning meaningful node representation in graph neural networks. Graph neural networks. Graph neural networks, which is known as GNN, is a neural network designed to operate on graphs. It generalizes traditional neural networks to non-Euclidean data. Each node updates its feature vector by aggregating information from its neighbor, combining topology and node feature. For example, social media node, which is where a user with features, for example, age, interest, layer one aggregation, average features from friends, updated non-features. Layer 2 aggregation consists of where it includes friends of friends, captures broader context, output. Node embedding for classification or recommendation is used as graph neural networks. Graph neural network extend neural network to graph structured data. Each node updates its representation by aggregating features from neighbors effectively capturing information. Popular GNN variant include GCN, which uses normalized adjacency matrices such as graph SAGE and GAT. Applications of graph neural networks. Graph neural networks have become more powerful tool for analyzing and learning from graph structured data. One of the primary applications is node classification, where the goal is to predict a label or category for individuals nodes based on their based on the feature and user interface and the structure of graph. For example, in graph networks, GNNs can predict user interests or behavior by aggregating information from their friends and friends of friends. It is also applicable for scaling the system and the graphs or the data, and also it is used in dynamic graphs. GNNs face challenges such as scaling to massive graphs and handling dynamic and volume data and providing interpretable embeddings. Future work includes hybrid architectures with transformers, self-supervised methods, and etc. Challenges. As graphs are irregular structure is an irregular data structure. Unlike images, graphs are non-Euclidean and irregular. And also, real-world graphs can have millions of nodes and edges, making storage and computational expensive. Over-smoothing and expressiveness. As graph neural network layers increase, node features tend to converge, making all nodes indistinguishable. Information from distant nodes get compressed into fixed size embeddings, losing important details. Computational and memory constraints. Large graphs uh, trained on massive graphs require batching, distributing processing, and etc. Dynamic graphs may require real-world graphs evolve over time, but handling updates efficiency is hard. Conclusion. Graph neural networks extend neural graphs to graphs, and multi-layer aggregation allows nodes to gather information and wide range of applications such as social networks, molecular property, and forecasting, etc. Challenges. Scalability, dynamic graphs, and interpretability are the main challenges. In conclusion, graph neural networks provide a powerful framework for learning from graph structured data. By aggregating information from neighbors across multiple layers, graph neural network can capture both local and global patterns. While challenges such as scalability and interpretability remain, ongoing research is hybrid architectures and self-supervised learning. Thank you.